How are you all doing this morning? All righty, so today we are going to talk about capacitance and so let's start with capacitance. I'm going to draw a picture here of what is called a parallel plate capacitor. So we have a terminal, connected to a metal plate, like so. And then there is a second metal plate underneath, for which we have another terminal. So I'm going to call this guy up top here, the top plate. I'm going to call this guy down here, our bottom plate. And in many capacitors, there is what's called a dielectric material that is located between the plates. So the capacitor forms kind of a sandwich. So I'm going to color all this stuff in pink in. We're going to call this guy the dielectric. And I'm also going to give you some geometric specifications for our capacitor. So it has a particular width, like so. The distance separating the plates will denote with the letter D. And we can say that the capacitor has a particular length, L, as well. And these geometric properties will come into play in just a little bit. Okay. So what a capacitor does is provide short-term energy storage for a circuit. If we were to apply a voltage across the terminals of our capacitor, we would observe that the capacitor would begin to collect electrical charge. Okay, so positive charge would accumulate on the top plate, which would in turn attract negative charge to accumulate on the bottom plate. Because the collected positive charge is physically separated from the collected negative charge by the dielectric material, an electric field will be generated between the plates, and this electric field is the energy storage mechanism of the capacitor. The charge separation also results in a difference of electric potential or voltage across the plate, where the charge Q will be equal to the capacitance C times the voltage V. So let me be explicit here. Charge, capacitance, and voltage. So we can actually rearrange this definition and find then that capacitance is simply the ratio of the amount of charge collected on the capacitor plate divided by the voltage across the capacitor, where the units of capacitance are coulombs per volt, which is the same as an amp second per volt, and we call this a farad. Measured in F. Okay. So the ability for a capacitor to store charge for an applied voltage, particularly for this parallel plate structure that I've drawn, is governed by two factors. the geometry of the capacitor, and the material properties of the dielectric. So much like a resistor, the capacitance depends on the shape. So we could say that C, our capacitance, is dependent on epsilon times W times L, so the area of the plate, divided by D, the distance that separates the plate. The geometric properties of capacitance are easy to describe, right? So the larger the area of the plate, the more charge can be physically collected on the plates. And the smaller the distance separating the plates, which is D, the stronger the generated electric field is. The material property which influences capacitance is the permittivity, epsilon, right here. So epsilon is really epsilon naught times epsilon r, where epsilon naught is the permittivity of free space, and it has a value of 8.854 times 10 to the minus 12 farads per meter. Epsilon r is what's called the relative permittivity, and that depends on the material. So for air, it's like 1.0006, so very, very close to what you would get with a vacuum between the plates. For silicon, it's 11.6, so if we put silicon between the two metal plates, we would have a stronger capacitor, so it could store more charge. And the relative permittivity of deionized water is actually 81, so we could put water, deionized water specifically between the plates, and you'd get a very, very large capacitor. That is actually something that I did in graduate school, was developed what's called a variable capacitor, which used electrostatic pumping to draw water in between the plates, and you were able to control the capacitance by how much water was in between them. So let's talk now about the circuit characteristics of a capacitor. So our schematic symbol for a capacitor is this guy. We have two terminals and a set of parallel lines representing the parallel plates of the capacitor. We could say that we have a voltage drop across the capacitor, VC, typically as a function of time, and we have a current flowing through the capacitor, IC, also as a function of time, and typically we denote the value of the capacitor in farads. So this is what I'm going to call a generic capacitor. And this is what we're going to be dealing with in this class the overwhelming majority of the time. But on some schematics, you might see the following capacitor symbol. So one of the parallel lines becomes a curved thing. This is what's called an electrolytic capacitor. And an electrolytic capacitor is a special type of capacitor that is polarized, meaning that if you apply the voltage across it improperly, it won't work. It'll actually break. We won't be dealing with those in this class, but you will absolutely see these electrolytic capacitors in all sorts of electronics. If you've ever opened up the case of your computer, most of those capacitors are electrolytic capacitors. You can get a larger capacitor value with them in a smaller physical space. But the drawback is that if you hook them up improperly, they pop. So capacitors obey the passive sign convention. So current flowing into the positive polarity terminal means that the capacitor is absorbing power, and current flowing into the negative polarity terminal means that the capacitor is supplying power. So the exact same rules that we did with resistors apply here for capacitors. Since electrical current, you may recall, is defined as the derivative of charge with respect to time. So I of t is equal to dq by dt. Well, we have an equation up here that's relating charge to capacitance and voltage. So that would be the derivative with respect to time of C times V. And assuming that our capacitor value cannot change, then what we get is C dV by dt. So the amount of current that flows through a capacitor is dependent on the capacitor value itself and the change in the voltage. Okay, so this is very, very important. If Vc of t does not change with time, Ic of t must be equal to 0 amps. So what does that mean for a DC circuit in particular? Because that's what we've been analyzing to this point. Any thoughts?
If it has no amps, if I is equal to 0 amps, then there wouldn't be a voltage on it, or it wouldn't be a voltage drop on it, correct?
No, not necessarily. So, for instance, if you hold a battery in your hand, like a AA battery, it would still have a voltage of 1.5 volts across its terminals, even though there's no current flowing through it. So, in a DC circuit, sorry, pen thing got wacky here. So in a DC circuit, capacitors behave like an open circuit, okay? So they can have whatever voltage drop needs to appear, but absolutely no current will flow through them. You may be asking yourself, well, why would you ever use a capacitor in a DC circuit? So all of our computers and all that kind of stuff are, even though they're real difficult and all that kind of stuff, those are just really big DC circuits, and capacitors are all over them. They help regulate power. They can be used in electronics to add AC signals to DC signals. They're used extensively in what are called filter circuits. And we'll talk more, actually, we won't talk more about that. We'll talk about it in circuits 2 for my other class, literally next week. All right. So, a question that I've been asked before, and it was, in my opinion, a pretty good question, is I'm going to scroll back up and we're going to look at this picture, right? So when I apply a voltage across this capacitor, charge starts to accumulate on the top plate, and we'll say positive charge is accumulating on the top plate and negative charge is accumulating on the bottom plate, but that charge is physically separated by that dielectric material. So a question that I've been asked before is, how does current flow through a capacitor if there is that dielectric material that's preventing the actual charge from passing from one plate to the other? And so it's all relative. And so what I mean by that is, when we're pushing charge onto the plate, it's moving. So we establish a net movement of positive charge. But the more charge that we put on the plate, the harder and harder it becomes, right? All those positive charges are going to try to repel each other. And so to get a lot of charge on the plate is going to require a very, very large voltage. Well, when we lower that voltage, so if that voltage changes and gets smaller, we'll see that some of those positive charges that are stored on the top plate will move towards the top terminal, causing current to flow in the opposite direction. And that's exactly what's described by this mathematical expression, okay? If we don't have any change in the voltage, that means that there's a fixed amount of charge stored on the plates. No current can flow through it. As soon as we change that voltage, either we're forcing more charge to add up on the plate, which is giving us positive current, or we're letting some of the charge off the plate, which is giving us negative current. But as soon as we try to move that charge around in any way, we observe that we get a current due to the change in voltage. All right, so we can do a little bit of mathematical manipulation of this equation, which I'm going to call equation 1. And if we rearrange it slightly, we'll find that the voltage across a capacitor is the integral from negative infinity to some point in time we're interested in of, 1 over c times the integral of IC t prime dt prime. I want to be clear, this t prime here is a dummy variable for time, so it does not indicate a derivative at all. We can also express this as 1 over c times the integral from t naught, some time where we know the value of the capacitor voltage, to t of IC of t prime dt prime plus VC at t naught. So this form is the one that we'll use most of the time in this class. Let me put a box around it. Call this guy equation 2, and I want to be clear about a couple of things here, okay? So we can say that a capacitor has memory. And what I mean by that is the current value of the voltage on a capacitor depends on a past value for the capacitor voltage, which is what this guy right here is. It's what we'll call an initial condition on the capacitor voltage. Without knowing what that initial condition is, we have to do this integral from negative infinity, where we assume that at the beginning of time, or whenever the capacitor was constructed or whatever, that there was no voltage present and that it was never connected to anything so that any energy got stored, okay? So we're gonna see these initial conditions pop up a lot in our next few class periods, and we will talk about how they relate to circuit theory a bit more. The power absorbed by a capacitor is, by definition, so I'll call this PC of T, is the voltage across the capacitor multiplied by the current flowing through the capacitor. And so this is going to become C times VC of T times the derivative of VC of T. Okay, so that's an odd little equation there because it depends on both the voltage itself and the rate at which the voltage change tells us how much power is absorbed by our capacitor. Since we have a mathematical description of power, we can then also determine energy. Let's call this guy equation 3. Actually, I'm going to go up and box the important equations here. So this guy was an important equation. This guy. Now energy will be the integral from negative infinity to T of PC T prime dt prime, which will be the integral from negative infinity to T of C VC dVC by dt. All these t's should be t primes, excuse me, dt prime. And so we can see that those two dt primes cancel each other out. And from this, we can change our integral slightly from VC at negative infinity to VC at t of C VC dVC, which gives us finally 1/2 times the capacitance times the square of the voltage, where we're assuming VC at negative infinity is equal to 0 volts. So our power equation gives us this energy equation, okay? So I've related the power in the capacitor to the voltage present across the capacitor. Similarly, I've now related the energy stored by a capacitor to the voltage drop across the capacitor. So when we're dealing with capacitors, the voltage present across the capacitor is the most important piece of information for us to know. If we know how the voltage is behaving, we know everything about the capacitor, okay? I'm going to do stuff in a slightly different order than I was intending to give us a example problem, I think. Sorry, give me just a second, please. All right, so let's work an example problem here. It's a good time for a break from all the theory that I've talked about. Let's say that we have a capacitor having a value of 0.2 millifarads. And we want to know the maximum amount of energy. So W max if our capacitor voltage VC of t is equal to 5 plus 3 away. Five plus 3 cosine squared. $200 T. All right. So we could, if we were so inclined, substitute this voltage VC of t into this equation, where we'd come up with a very gnarly and ugly looking mathematical expression for what's going on here, right? That is absolutely one way we could substitute it in. And then since we're looking for the maximum value, we would substitute it in. So we would square that guy and all that kind of good stuff. Then we'd have to take the derivative, set it equal to 0, and figure stuff out. But instead for this problem, let's think about this guy a little bit more critically, all right? So let me ask you guys a question here. Does it make sense for the maximum energy stored in a capacitor to happen when the voltage is at its highest value, so most positive, or when it's at its lowest value or most negative? Most positive. So because it's squared, the most positive value or the most negative value would be appropriate here. So what I mean by that is this isn't our waveform by any stretch of the imagination, but let's say that I had, I'm going to call this VC2 of t. Actually, I'm going to draw it as a picture. So this is time. This is a different capacitor voltage waveform. And let's say that it looks something like this. Find out shortly that it literally can't look like this, but for now, we can pretend. And let's say that this was 4 volts, and this guy down here was -6 volts, right? So our capacitor would be storing the most amount of energy whenever we hit the larger peak of the voltage, right? So for example, when VC of 2 is 4 volts, Oh, so for any time where WC is 4 volts, or at any time, let me redraw this. WC when VC is equal to 4 volts. There we go. That would be 1/2 times 0.2 farads times 4 volts quantity squared. So that would be 0.5 times 0.2 times 10 to the minus 3 because we're dealing with millifarads. So I need to rewrite that. 0.2 millifarad times 4 volts squared. We would be absorbing 1.6, millijoules of energy. But whenever VC is at -6 volts, we have 1/2 times 0.2 millifarads times -6 volts quantity squared would give us 3.6 millijoules. So when the magnitude of the voltage at its highest value, we see that the energy stored by the capacitor is also at its highest value. Okay. So with that in mind, for this voltage VC of t here, what is the maximum value that it could ever have? Anybody have any thoughts on how we might determine that? All right, so let me ask you guys a question. I'm going to come up here. We're going to figure out what VC max is. All right. So we could break this function down into parts. All right. So it has a 5 volt DC offset, and then there's a 3 volt cosine squared term effectively on top. All right. So let's look at the DC part. All right. What's the maximum value that the 5 volts of DC voltage could ever contribute?
What are they, just 5 volts?
Yeah, nothing real weird there. 5 volts is a constant, so that's what it's going to contribute at all times. Okay. Now we have to deal with this sinusoidally varying part. Okay. So let's not worry about the 3 just yet. What is the maximum value of a cosine function?
Would it be 1?
1. Yeah. So cosine, by definition, ranges from 1 to -1. It just cycles 1 to -1 over and over and over again as time increases. Okay. So if the maximum value of a cosine function is 1, then what is the maximum value of cosine squared?
Just 1.
Just 1. All right. And so that is being multiplied by a factor of 3. So we would have 5 volts plus 3 volts times 1 squared means that our maximum value for our voltage here is 8 volts. Seem reasonable?
Yes, sir.
Right. So what we're going to see is that every time this guy hits its positive peak, we're going to have a maximum amount of voltage that's being the maximum amount of voltage will be being applied across the capacitor's plates, and therefore the maximum amount of energy will be being stored by the capacitor. So let me just scratch through all this. I was just trying to illustrate a point with that.
That factor of 200 not have anything to do with it? Like, would that not?
That's a fantastic question, okay? So that 200T, that is the angular frequency. So that's telling us how quickly the sinusoid is oscillating, but it has nothing to do with the amplitude whatsoever. So just as a very, very brief review of sinusoids, we'll get into this much more in about a week and a half. That's a very good question, though. So we have a cosine function, right? So I can say pretty easily cosine at t is equal to 0, it's going to start at its maximum value, so up here, and then after 1/4 of its period, it's going to come down here to be at 1/4 of its period, it'll hit 0. At half of its period, it'll hit -1. At 3/4 of its period, it will oscillate back up to 0. And after exactly 1 period, it'll come back to 1. And that just repeats over and over and over again. All right. So the period of this cosine function is defined as the amount of time it takes to go from its maximum value back to its maximum value, or we could define it as minimum value to minimum value, or we could do 0 crossings as well, but you got to pay attention to that, okay? You guys learned in engineering 121 that the period of a sinusoidal function is inversely related to the linear frequency. So period is the time it takes for a cycle to occur, and the frequency is the number of cycles per second. Well, that 200 up there is what's called the angular frequency. Omega is equal to 2 pi times f. All right. So this sinusoid right here, let's just call it A naught cosine omega t. So it has some amplitude value, A naught here. So that's the distance away from the 0. And its negative peak is negative A naught. Omega is just related to how quickly this thing is oscillating. It has nothing whatsoever to do with the amplitude at all. Okay, so very, very good question. The cosine, the 200T part has nothing to do with the maximum value. It's just if I'm stretching this cosine function out or I'm compressing it together, that's all it has stuff to do with. So P max in this case will then be 1/2 times 0.2 millifarads times 8 volts squared will be 6.4 millijoules. And we got that without having to do any of the hard calculus, and it would be reasonably difficult because we'd have to pull out several trig identities to make sense of that guy and be able to take the derivative of it easily. Okay. Let's look at another one that's, I guess, a little bit more straightforward. So let's say that we have that same 0.2 millifarad capacitor, and we pass a current, or we observe a current, IC of t is equal to 8 e to the minus 100t milliamps for t is greater than or equal to 0 plus, and I'll explain what I mean by that in a moment. And we are also given the fact that VC at 0, or VC of t, is equal to 0 for t less than 0 minus. So graphically, what our capacitor let me think about this. Okay. All right, so this guy right here is really just giving us our initial condition, right? If we wanted to figure out what the capacitor voltage is as a function of time for t greater than or equal to 0 plus is, we need to know how IC behaves at t greater than 0 plus, and we need to know what the voltage was in the past, so prior to us looking at things. So for this guy, since we know what the current is, our equation that we would use would be the 1 over c integral from t naught to t of IC of t prime dt prime plus VC at t naught, okay? So this VC at t naught stuff, that's this guy right here, and our IC is then obviously this guy right here. So we would have the integral of 1 over 0.2 millifarads. So that would be 0.2 times 10 to the minus 3. Let's look at the units of millifarads real quick. Where did I get my units? There we go. So amp seconds per volt, excuse me. Amp second per volt times the integral. T is equal to 0 seconds to some later point in time that we are interested in of 8 times 10 to the minus 3 amps e to the minus 100t dt plus 0 volts. So I'm going to take that 8 milliamps and move it to the other side so that I have 8 times 10 to the minus 3. It doesn't look like a 3. Amps times 1 volt divided by 0.2 times 10 to the minus 3 amp seconds. So I can see that my amps cancel my amps there, so I'm left with volts per second integral from 0 to t of e to the minus 100t dt. So how do I take the integral of an exponential?
Isn't it just negative 1 over 100 e to negative 100 t?
So 8. The times 10 to the 3 is going to cancel each other out, so I'm going to get rid of that. So I'm going to have 8 volts over 0.2 seconds. So you suggested that it was negative 1 over 100.
Yeah.
E to the negative 100 t prime evaluated at
0 to t.
0. Yeah. Okay. So you're absolutely correct, but we have to pay attention to one thing here. And this is another place where it's not intuitively obvious. So we got to think about it. Mathematically, you are 100% correct. All right. So e to the alpha t, the derivative of e to the alpha t is, sorry, the integral of e to the alpha t is 1 over alpha e to the alpha t plus c, because I have an indefinite integral up there. What are the units on alpha here? We have negative 100. What are the units on that? Any thoughts?
Would it not just be unitless, since that e to the negative 100t didn't have any units with it?
So e to the negative 100t by itself is unitless. You're correct there. The exponential is unitless. But that means, so t is representative of time, right? So let's just say arbitrarily that t is in seconds. That means that alpha has to be measured in units of per second in order for the exponential function to act on a unitless expression, which is what's required. Right? Because how would you take the number in volts? All right. On the exam or something like that, I will usually explicitly give you the units of things like that, but I just wanted to kind of talk you guys through it to make sure that it was making sense to you. So now we have negative 8 volts over, let's see, 0.2 times 100 would be 20. E to the minus 100t minus e to the 0. So this would look like 8 over 20 is 0.4. So negative 0.4 e to the minus 100t plus 0.4 volts. So this is our capacitor voltage as a function of time based on this exponential current flowing through our capacitor. Let's say that I have the following graph. where this would be 15 milliamps. This would be -5 milliamps. And let me put some units on here. 2 seconds, 4 seconds, 6 seconds, 8 seconds, 10 seconds, etc. So this is obviously time measured in seconds. This is IC of t measured in milliamps. And this is the graph of the current flowing through a 5 microfarad capacitor, where this is VC of t, and this is the direction of IC of t. How would we determine the power absorbed by the capacitor? So we want PC of t at t is equal to 3 seconds. I like to ask graph questions like this on the exam. So we're given current. Oh, and I guess we also need to know VC at 0 seconds is 0 volts. We need to know an initial condition, okay? So if we're ever given the current, whether it be a mathematical expression or a picture, we're going to go back to that equation that we just used. VC of t is equal to 1/c integral from t naught to t IC t prime dt prime plus VC at t naught. We're told that this guy right here is 0 volts, so we can effectively throw that away. So we need to integrate this graph. What does that mean?
I should just be able to find the area under the curve up to 3
Exactly.
seconds.
Exactly right. So at t is equal to 3 seconds, would be this vertical line that I've just drawn. So all we really need to do is figure out the area of that triangle, and then figure out the area, let's call that A1, and then figure out the area of this rectangle, let's call that A2, and we'd be good to go, right? So we could say then that VC of t is equal to 1/c multiplied by A1 plus A2, because A1 and A2 represent the integral over that time period from 0 seconds to 3 seconds, right? So that would be 1/5 microfarads. How do we determine what that area A1 is?
Just 1/2 the base times the height, where your base is from 0 to 2 seconds, and your height is 0 to 15 milliamps.
So 0 to 2 seconds, so that's going to be 2 seconds. And the height is 15 milliamps, all right. What is A2?
The the area of the rectangle from 3 seconds, like 3 minus 2 seconds, so 1 second, and then the height is 15 milliamps.
All right. It's Mr. Gray that's talking, right?
Yes.
Okay, you're doing a wonderful job. I just wanted to let you know you're doing great. All right, so let's go ahead and do some math here. What do you think the voltage is going to turn out to be here? So we have 1 over 5 times 10 to the minus 6 times 0.5 times 2 times 15 times 10 to the minus 3 plus another 15 times 10 to the minus 3. Give me 6,000 volts. I did my math correctly, which I believe I did. So 6,000 volts. Is that the answer that I was looking for?
No, you wanted power.
Right, but to know power, I need to know voltage, which we just figured out, and current. So somebody else, because Mr. Gray's doing too good of a job, tell me what my current is at T is equal to 3 seconds.
Would that be the 15 milliamps?
Exactly right. You just read it straight off the graph. No math required. And so my power at T is equal to 3 seconds is just the product of my voltage and my current. So that'd be 6,000 volts times 15 milliamps would be 90 watts. All right. So let me scroll back up here real quick. Okay. Yeah. These 4 equations that I've circled or blocked in blue, and I've also denoted them with stuff in parentheses or numbers in parentheses, really are these are all of the mathematical expressions that you will possibly ever need to analyze pretty much any circuit involving capacitors and inductors. Okay, there is we looked at this guy right here and observed that when there is no change in the voltage, so for a DC circuit, the capacitor behaves like an open circuit. We use that guy to develop the equation for the current, for the voltage in terms of the current. From there, we went to power. From there, we went to energy. The only other relationship that we have to worry about here specifically is actually dealing with that first equation again. So let me draw a line here, and we're going to talk about one other brief little topic having to do with capacitors. I'm going to write that equation down. IC of T is equal to C dV by dt. Okay. So let's say that I have the following voltage waveform Vc of T, and I want to figure out how the current through the capacitor is behaving. And we're going to do this problem specifically where C is equal to 1 farad, just to make the math easy. All right. So this will be IC of t. So let's say that our capacitor voltage ramps up like this, stays constant, and then ramps down like so. So it has a value of, let's call it 5 volts at 2 seconds. And then at 4 seconds, it starts decaying down to 0. What would our current look like? Anybody have any thoughts? All right, let me ask you guys a question. Let's look at the current specifically over the time interval from 2 seconds to 4 seconds. Okay? So over the time interval from 2 seconds to 4 seconds, is my voltage changing?
No, it's constant.
No, the voltage is constant. So what does my capacitor current have to be?
Constant as well.
So use the equation right here and try again. Because I mean, it will be constant, but it'll be a very specific constant. What's the derivative of 5 volts with respect to time?
Would it be constant at 0?
Yes, it'll be 0. That's exactly right. It'll be 0 over that whole interval, right? So if this, oops, that's not what I wanted to do. So this is 2 seconds and this is 4 seconds. Our capacitor current will be 0 between 2 and 4 seconds because the voltage isn't changing. So now let's back things up a little bit. Let's look at the time interval from 0 seconds to 2 seconds. Is the capacitor voltage changing? As a function of time?
Yeah.
Yes.
Yeah, it's increasing, right? As t gets larger, that voltage is getting larger and larger and larger as well. So what is the derivative of the voltage with respect to time, which is just the slope?
Five over 2.
5 over 2, right? 5 volts over 2 seconds. So 2.5 volts per second. When we multiply that by 1 farad, we would get 2.5 amperes. So over this particular interval, it is 2.5 amps. And then the current is going to abruptly drop down to 0 amps when the voltage goes constant. So let's look at the time interval from 4 seconds to 6 seconds. Is the voltage changing?
Decreasing.
Yeah, it's decreasing. So what is my slope?
Negative 5 over 2.
Negative 5 over 2. Multiply that by my 1 farad, and I see that my voltage is going to be negative 2.5 amps. Okay. So we have observed that when the voltage is increasing, the current is positive. When the voltage positive, but since it's increasing at a constant rate, the current has a constant value. When the voltage is constant, our current is 0. And when the voltage is decreasing, it's negative. And because it's decreasing at a constant rate, it is a negative constant. So let's say I took the same waveform. where this is dc of t, this is t, and over here will be my current. So this time at 1 second, it goes up, stays constant, drops down. So this is 2, this is 4, 5. So this is still 5 volts. How should my current waveform change?
Should just start at 1 instead of 0. Same thing.
Okay, so roughly the same thing. All right. So it'll start at 1 instead of 0. I agree with that. So I'll have a block like this. Then it'll be 0 for 2 seconds. So something like this, where this is 4 seconds, this is 5 seconds. What's this value of the current going to be? What's its maximum value? Because our slope has changed, right? We're increasing at twice the rate. So before we had a slope of 2.5 volts per second, now we have a slope of 5 volts per second. So we should see that since the voltage is changing twice as quickly, we get twice as much current. So 5 amps and negative 5 amps. And if we further increased the rate at which the voltage changes, we'd see that we get more and more currents. So now we get to the important bit. What's going to happen to my current if my voltage waveform shifts from 0 volts up to 5 volts instantaneously? Any thoughts? What's my slope as we approach 2 seconds from the left?
Should be just 0 or 1. Wait, approach 2 seconds from the origin to 2 seconds.
Yeah, but I'm saying so like a fraction of a second before 2 seconds. Effectively, I want to know what my slope is here, right? So it's my change in voltage, which is 5 volts, divided by my change in time, which is infinitely small. So what's my derivative?
Should just be 0.
I disagree. Right? My change in voltage is 5 volts. My change in time is 0 seconds. What's 5 divided by 0?
Undefined. Or
Undefined, technically, sure. I would argue that it's infinitely large. Right. So what if we didn't look at 0 seconds? We looked at we say that it took 0.000000001 seconds or something like that to change. We would find that our voltage is going to get so. When we started off, we had a well-defined slope. We increased the slope and saw that the current increased. Now we are in a situation to where the current, or excuse me, the voltage is increasing in an infinitely small amount of time. And so what we will observe is that at t is equal to 2 seconds, we have an impulse function. Okay, so that means the current is infinitely large at t is equal to 2 seconds. And then at t is equal to 4 seconds, the current is infinitely large, but also negative. Okay, so is it possible for us to have an infinitely large current?
I would think not.
Right. An infinitely large current would mean that an infinite amount of charge, which we know can't happen because of physics, would be passing through a point in an infinitesimally small amount of time. Okay. So what happens here is if we cause our capacitor voltage to change abruptly, we kind of break physics. So what we can say then is that the voltage drop across a capacitor cannot change abruptly. All right. So let me be very explicit about what I mean. We have a voltage. Let's say it's 5 volts. And then it drops down to 0, like so. You cannot have a situation like this, okay? But we can absolutely have a situation like this, where there is a fixed non-infinite slope. So the reason why I'm making that distinction is that we don't have to have smooth curves, right? We just can't have a discontinuity. So as long as we don't have a discontinuity where the value of our voltage has 2 different values for the same instant in time, everything is okay. We're going to actually wind up using this statement, the voltage drop across a capacitor cannot change abruptly, an awful lot when we get into what's called transient analysis, which is our next big topic. So after we finish up capacitors and inductors on Monday, so just starting on Tuesday, we'll revisit this guy an awful lot. Okay, so let's circle back around to something a little bit more practical than all this heavy, heady theory junk I've been throwing at you guys. Circuits can contain more than one capacitor, so it might be useful for us to understand how to combine them. So let's say that I have a network containing multiple capacitors connected in series. Let's call this guy C1. And so we'll have an associated voltage drop, VC1. Then I'll have a capacitor C2, which will have an associated voltage drop, VC2. And out here, I have a capacitor Cn, which will have an associated voltage drop, VCn. If I have some source voltage VFT acting on this system. So, since all of the capacitors are in series, it should be easy enough to see that they will all have a current I of t flowing through them. So they'll all have the exact same current because they're all connected in series. That has to be true. So if we apply Kirchhoff's voltage law around our loop, what we'll find is that V of t is equal to VC1 of t plus VC2 of t plus VCn of t. Which would be 1 over C1 times the integral from negative infinity to t of I of t dt plus 1 over C2 times the integral from negative infinity to t of I of t prime dt prime plus 1 over C sub n integral from negative infinity to t of I of t prime dt prime. Right? So all of those integrals are identical. So I could express this as 1 over C1 plus 1 over C2 plus 1 over C sub n times the integral from negative infinity to t of I of t prime dt prime. And I'm then going to call that combination of capacitances the equivalent capacitance. Where CEQ is that sum 1 over C1 plus 1 over C2 plus 1 over C sub n to the negative 1 power, or more formally, the summation from k is equal to 1 to n of 1 over C sub k to the minus 1 power, or in an even more succinct form, capacitors in series add like resistors in parallel. If instead I have a network having some fixed voltage EFT across it, some current IFT entering it, and it contains a number of capacitors connected in parallel. So let's call this guy C1 and this current IC1. I will be C2 with some current IC2. This current will be C sub n with associated, or excuse me, that capacitor will be C sub n with an associated current ICN of T. Like so. If I apply Kirchhoff's current law, I can see that IC of T is equal to IC1 plus IC2 plus ICN. I can relate all of those currents to that common voltage over everything. So that would be C1 dV by dt plus C2 dV by dt plus Cn dV by dt. Grouping like terms, I have C1 plus C2 plus Cn, all multiplied by dV by dt. Looks like Ceq dV by dt, where Ceq is equal to C1 plus C2 plus C sub n, or simply the sum. That is a terrible looking summation. K is equal to 1 to n of C sub k, or capacitors in parallel add like resistors in series. So that is how we can combine and find equivalent capacitances in networks that contain more than one capacitor. Okay, so capacitors in series add like resistors in parallel. Capacitors in parallel add like resistors in series. I do not expect you guys to memorize that derivation by any stretch. If you can remember this guy right here and this guy right here, you're good to go with combining them. Okay, any questions regarding this material? I know we worked some funky looking example problems. I'm going to be spending this weekend setting up all of the practice problems for you guys to use to study for your next test and all that kind of stuff. So yeah, what else do you want to talk about today? Sounds like nothing. All right. If there are no questions, then I will see you guys on Monday afternoon, where we will talk about inductors. That lecture should be fairly short with regards to the new material, because as we'll find, inductors and capacitors behave extraordinarily similarly. And so we'll start working some circuits that contain both capacitors and inductors and talk about all that kind of good stuff. All right, so I'll see you guys on Monday.